Hi there. In this video, we'll look at an optimization problem. And the problem I selected comes from 4.4 of your textbook, Modeling and Optimization. This problem can be found on page 226, and it is problem 10. This is actually my second take at this video. Number one, I thought the first video was too long, although I have a feeling this one's going to be pretty lengthy as well, because there's an awful lot to do and a lot to say. But the second thing and main reason I'm redoing it is to try to present a more organized solution. And I hope that that helps you. Here it goes. So in this problem, we are given a 216 square meter rectangular pea-patch. We want to enclose that pea-patch with a fence, and we want to divide into two equal areas in such a way that the fence that divides the areas runs parallel to one of the sides. And our task is to determine what are the dimensions of the outer rectangle such that we'll need the least amount of total fence. Imagine that the fence costs money and you don't want to spend more than you have to. All right, and ultimately, this is the main question. How much fence do you need to enclose this much area? All right, so with that, let's get started. First of all, just vocabulary. What does optimization mean? The word optimum means best. Okay, it means ideal. The word optimal means best. Most favorable conditions. Okay. All right, so that's just vocabulary point. All right, and so we're told, here I've condensed the wording here to the main idea, which is that the area of our rectangular region is 216 square meters. We want to divide that region into two equal parts. So I went ahead and did that here. And we want to determine how much fencing is needed. Okay. Now, general comment about all these modeling and optimization problems. You should make it your goal to develop a model, find an equation that's represented with a single variable. If you continue your studies of calculus, you'll learn multivariable calculus, but until that time, you need to figure out how to get things down to one variable because that is all you know. All right, so let's pursue that goal. And in pursuit of that goal, let's just try to get a feel for the problem. And the first inference that we might make with that is this. Knowing that we've divided this much area into two equal parts, we want the value that makes a total of 216 and is equal to the other value. So that tells us that each little plot needs to have 108 square meters of area. Okay, so that's where this information is coming from. All right, now many ways to enclose that area. You could have a very short distance multiplied by a very long distance to achieve that area, or something in between, a little taller, a little less wide. It could be almost two squares next to each other. It could be longer this way, shorter this way. Many, many ways that you could arrange this fencing to enclose this area. All right, now let's get specific with one or two examples, and it's helpful to use a calculator for this part. Remember, the goal is to make each sub-rectangle have this area. Okay, so let me just go ahead and start throwing in a couple ideas. Start with an easy one. What if it's 1 meter tall? So what if I'll call that the length. What if the length is 1? What would the width from here to here need to be to make an area of 108? Well, obviously, 108. Okay, and with that, can I see how much fence is required to do it in this way? Well, there's another 108 this way, another 1 this way. There's the divider, which requires 1 meter of fencing. Here's another 108 meters of fence. And finally, another 108 meters of fence. And I'm just going to wheel out my calculator and see how much that is altogether. Looks like 435 meters of fence would be needed to enclose it if it's 1 meter high. Okay, but let's see if we can do better than that. That is probably going to be pretty costly, and I think we can beat that. All right, let's try a couple more specific examples. So what if I'm 2 meters tall? What happens now? If the length is 2, what does the width have to be to have an area of 108? Well, 54 times 2 is 108. So the width would be 54. And let me just see if I can compute how much fence is needed for that. I'm getting 222 meters of fence. Notice right there, by doubling this dimension, the height of the rectangle, we cut the amount of fence down by an awful lot. So you would save a ton of money just by avoiding this and instead using this. But I think we can do even better. Let's just do one more specific example just to really get a feel for what's going on with this. And can I try something more extreme? Let me see what I can work with here. How about, looking for some whole numbers here. Oh, I don't know. How about 8? Okay. If the height is 8, the width would have to be 27 to have a product of 108. And so let's see what happens if I use 8 and 27. Using my calculator to compute this many of these and this many of these, I'm getting 132 for that. Okay, so just by trying a few specific examples, I was able to determine that I can get the amount of fencing down pretty easily to around the 130 marker. But can we do better? And what is the optimum way to fence this area? That is our question. Okay, so with that, I think we're in a good position now to develop that model. We'll need to use a variable. Not knowing what the optimal height is, we'll call it x. And so here's x again. We'll call the width y for the little subrectangle. And then we're looking at this scenario. Okay, now let's count things up. Let me write big F for amount of fencing. And I can easily express that as a two-variable function as follows. How many x's? 1, 2, 3. So 3 times that amount of fence. Plus, how many y's? 1, 2, 3, 4. So I need 3 x's and 4 y's, and that will give me the total amounts of fencing. Okay, this is a two-variable model. As I said earlier, you will not be able to work with the two-variable model unless you know multivariable calculus. So you might as well try to eliminate one of the variables. And so let's go there. Well, what else do we know? We know that the area is 216. So can I write an equation for that? Let's call this part 1, part 2. The area, also a function of the length and width. Okay. And we decided that 2 of these would require 108 each. So we know that the product of x and y must be 108. So we can write the product of x and y is 108. Okay. And now we've got a representation of the area as well as the amount of fencing. And what we want to do is just combine these two ideas together. So let me combine these in such a way that we get a single variable model for the amount of fencing. Okay, and the way to do that, if I can just clean this up for you briefly so you can see everything with that. Okay, let's see here. Great. All right, the way to do that is to just operate on this guy right here. Okay, let's eliminate one of the variables. We can express y as a function of x by dividing both sides by x. Or I could have done it the opposite way, express x as a function of y by dividing by y. Your choice. Okay, so now what I can do is return back to this guy, the fence function. But this time I'm going to write him as a single variable function because we're going to eliminate y. Alright, so I'm keeping 3x. We've got 4 times y. But what we'll do is we will substitute instead of y, let's write the expression for y, which is 108 divided by x. Okay, and now we've succeeded at creating a single variable model for the amount of fence that's needed. Okay, and this will be important. This is a major development in our solution of this problem. Okay, goal 2, we need to establish some constraints on the inputs to this function. If there are any, we should find them, and that will affect how we proceed to solve this problem. Well, if we just click over here, we saw earlier, you can have a very short and wide rectangle to achieve the desired area. You can't have a distance of 0, or else it would have no area. So a lower bound should be 0 for sure. And anything else? Well, not really. I could even make this be like 1/100th. As long as I choose a sufficiently large value here, I can make the area come out to 108. Okay, so this is actually the only constraint. X has to be positive. Other than that, we are free to plug in whatever value we want. So constraints, X bigger than 0. Okay, with that, we're ready to move to towards the goal of finding the optimal fencing arrangement, meaning what's the least amount of fencing that we can get away with. And so that would be a question of calculus. All right, now let's review strategies that we've learned for finding the minimum value of a function in general. Okay, so basically this amounts to breaking it down into two scenarios depending on what kind of interval you're dealing with and what kind of domain you have. If the domain is some closed bounded interval that starts somewhere and ends somewhere definite, okay, then we have a very simple strategy which amounts to plugging in the endpoints into the formula, finding the critical numbers and plugging them into the formula, and then just picking the smallest. And that's guaranteed to be the minimum. That's called the extreme value theorem and is very simple to execute if you can get away with it. However, if you don't have some definite interval where you start somewhere, stop somewhere, if your interval is an open interval or if it's unbounded, such as this one here, then you have to resort to a different kind of logic. And in particular, we should keep in mind, first of all, let me make you a drawing. Let me just back up a stage in terms of this. All right, this is just showing that, hey, your min could be at a critical number or possibly at an endpoint. All right, so that's just the drawing that goes along with situation A. Situation B, however, okay, let's keep in mind, first of all, not every function even has a minimum, for one. All right, so that if you're looking for a minimum, there might be none to be found. So that's just something to bear in mind. If there is a minimum, though, here's how you go about finding it. You again need the critical points, so you'll need a derivative for that. But then you'll need to use the first derivative test, okay, to actually logically establish that the value found is a minimum. Because, of course, maybe it's a max. Maybe it really is the min. Or maybe it's none of those things. Maybe it's like a shelf point. Okay? Or maybe they're like other min and max points, and you need to know which one is the least. Okay, so there's some logic to work through, and we will work through that in this example. Okay, let's get started. So here goes. We're going to need to find critical points. So that means we're going to need to take the derivative, which is what this chapter is all about. What can you do with derivatives? Well, you can solve a p-patch problem for one. So let me go ahead and compute f prime. Derivative of 3x, 3. Okay.
Mr. Ogantanya, please go to the counseling office. Mr. Ogantanya.
It occurs to me when I'm working on this term right here, maybe I'll just multiply 4 by 108 and simplify that. So this is 400s and 4/8, which is 432. And now we have something that's a little easier to work with. Okay, now in preparation to take the derivative of this guy right here, let me go off to the side here and just do a little scratch work. So just use your exponent rules. Bring the power down for derivative. -1 times 432. Knock the power down a step. And then rewrite it in exponent form using fractions. Okay, so these are all equivalent, and we've just used the regular power rule. And we got -432 divided by x squared. Okay, and I'll clean up this area right here, my scratch work. You get good, you can do that mentally. All right, and here's an expression for the derivative. Okay, so what's next? Well, what can we learn from the derivative? Well, if we can figure out where it's 0, we might be able to locate that minimum point. So let's set the derivative to 0 and then solve the resulting equation. Okay. All right, I feel like I'm going to need a little bit of room for this, so let me just shrink this down for you a little bit. There we go. And now I can continue. All right, so to solve for x, we need to add this term to both sides. So we get 432 divided by x squared equals 3. Let me just run over here with this. Now we can multiply both sides by x squared, giving 432 equals 3x squared. And if we just divide both sides by 3, we get, let me pull out my calculator, 432 divided by 3 is 144. Equals x squared. And so x must be 12. The square root of 144 is 12. Okay. And let me double check. Yep, looks good. Okay. So with that, we've now found the critical number for this function. And now it's time to use the first derivative test, which will allow us to ascertain whether that critical number is a minimum, a maximum, or none of the above. Okay, so let's get started on that. Okay, first of all, we agreed that the lower bound for the inputs is 0, so let me mark that. There is no upper bound, so we're going all the way to the end of the number line over here. And we determined that the critical number for this function is 12. So I'll label that here. Okay, time to start throwing in values and figuring out what f prime looks like for those values. So we've agreed if you plug in 12, you're going to get 0. Let's try a number higher than 12, like 13. So let's see, 432 divided by 13 squared is this number, and I got 3 minus 255. Okay, and there are ways to reason these things out. If this is a big, big number, then when you divide, it'll be small. And so the answer should be positive. Okay, which it is. All right, so when you plug in numbers higher than 12, your derivative will yield a positive answer. Okay, and if I plug in a number less than 12, let's take 1 for example, we're going to be dividing by a small number, so the answer will be fairly large. And for instance, if I use 1, you get 3 minus 432, which obviously is a negative quantity. All right, so that just goes to show when you plug in a number between 0 and 12, you're going to get a negative derivative. Okay, and now we need to formally state what ends up being obvious visually. The function is going to decrease and then increase, and therefore this is a min. But we need to get real formal about this. So the expectation of the College Board with your AP tests is that you write sentences that sound something like the following. Let's see. I'll put around x equals 12. F prime changes from negative to positive. From left to right, it changes from negative to positive. And what does this mean? It means the output at that input is a minimum. Okay, and probably technically I just showed that it's a local minimum. If you want to prove that it's the absolute minimum, you would need to state the derivative is negative right up until 12. So it's decreasing all the way up to there. And then the derivative is positive from 12 to forever. So it's increasing forever after. Okay, so I'll just say that rather than write it, but it's going to decrease forever up to there, and then increase forever from there. So therefore, it is, in fact, the absolute minimum when x is 12. Okay, so now we're at the point where we can answer the question, how much fencing is needed, having determined that this value should be 12. Okay, and so let's see, what would be the width of these rectangles? Remember that we're shooting for a target area of 108 for each small rectangle, so that the total area is 216, which was given to us in the problem. So I'm wheeling out my calculator. 108 divided by 12 is 9. And so we get 9 for that. Okay, so we want 12 by 9 subplots, and that should minimize the amount of fence needed to enclose this area. Let me go ahead and write these in all the way around and clean up the additional information. Okay, so we have how much fence altogether? Okay, we have 3. Maybe I'll just write it in a way that's clean and clear. We have 3 of these 12s running up and down. 1, 2, 3 12s. And then we have 1, 2, 3, 4 components of size 9. And so, grabbing a calculator again. Oh, maybe I don't need to. This looks easy enough. 3 12s makes 36. 4 9s also 36. And so, we get 72. So it appears that we need at least 72 meters of fencing to enclose a rectangle with area 216 in such a way that there are 2 equal regions and a fence running around the border and down the middle. And that's my solution to this problem. Okay, let's pop over to Desmos and see if the graph supports our analysis. Okay, so I just typed in the fence function. We need 3 running vertically and 108 divided by x running horizontally with 4 of those components. So that is the formula for the function. And let's just try to see the graph. Got to zoom out for a while. And there's the graph. Okay, let's adjust our x's so that the graph uses more of our screen. So let's go negative 50 to 50. Whoops, 50. Okay. All right, so this is what the graph looks like. This negative amount of fencing is not making a lot of sense, so let's restrict it so that x has to be a positive number. And now we can just focus on this part of the graph. Okay. Notice if you use a small value of x, which meant your rectangle was short, the amount of fencing is just getting higher and higher. All right, so you can use as much fence as you want. You can use 500 meters of fence if you want to. All right. On the other hand, if you make a really, really wide or tall rectangle, again, the amount of fencing is just unlimited. Okay, but we'd like to use our money well, so let's aim to use the least amount of fence. And Desmos is telling us the least amount of fence happens when x is 12 and the amount of fencing required is 72. I believe that exactly agrees with our answers. Here's 12, here's 72. And so that confirms that our work is correct. All right, so let's just recap, putting it all together just very quickly here. We developed, first we just inferred each one has to be 108. We got a feel for the problem, tried a few cases, and by the way, notice that the actual optimal, let me just write this in, the optimal dimensions were 12 by 9 for an amount of fencing 72. This is like way, way better than any of these that we ran earlier. So this is optimal right here. Okay, so recapping the math that was involved, we chose some variables, we wrote a fence function, an area function, isolated one of the variables, plugged that variable in, and that gave us a single variable expression for the amount of fencing. We found that the constraint on x is that it must be a positive number. We then used calculus by taking a derivative. To find the critical points, we set that to 0, did some algebra, found the value of x, which was 12, which is the critical number. And it occurs to me, I didn't even bother about this, just an oversight, but there's actually 2 values that make this work, which are 12 and negative 12. It's just that, again, that negative one doesn't make sense in the problem, so it didn't end up mattering. Okay, we then used the first derivative test to prove that the critical value we found is actually a minimum. And so we went back to the problem and found the amount of fence that goes along with that, the length and width of the rectangle to achieve that, and we solved the problem. Really hope that this is helping you to solve, to learn how to do modeling, and to solve optimization problems. See you next time.